To finish off the chapter, we're going to talk about something called real gases. We made certain assumptions in the ideal gas equation based on the kinetic molecular theory. One assumption that the container volume is relatively large, so the gases can be really far apart from each other. We assume that the gases themselves occupy very, very little space. We usually just assume that the volume available to the gas is the entire volume of the container. So we don't really think about the fact that the other gases are taking up space because their volume is so small compared to the volume of the container. The second assumption we make is that there's no intermolecular interactions between the gas particles. These assumptions are true as long as the temperature is high, because when you have the gases at high temperature, they're moving very fast, right? Remember that the temperature relates to the kinetic energy, which relates to the speed of the gases. And if they move very fast, then there's really no significant interactions between the molecules. The second condition that has to be satisfied is the pressure has to be low. Low pressure really means that there's not a lot of particles. That means you pretty much have large volume of the container relative to the number of particles that you have. So that satisfied this assumption right here. What happens when we don't have this condition? We have low temperature and we have high pressure, okay? The person who actually studied this was Johannes van der Waals. You can see it in the graph here that's comparing the behavior of gases at the ideal condition, which again is the high temperature, low pressure condition, versus what we refer to as the real condition, which is the low temperature, high pressure condition. There's a line that's horizontal line here at 1. So that's the expected behavior for an ideal gas. This y-axis here is PV over RT for 1 mole of gas. In theory, this should equal to N, and if N is equal to 1 mole, then the value should always be 1, whether you're changing pressure or not. But what you see here for actual gases, as you increase pressure, you see that the value of PV over RT actually changes quite a bit. For helium, it goes all the way up here. Water actually drops down all the way here. So none of them is actually near the ideal gas line itself. They're only close to the ideal gas line when you have low pressure, which is the pressure in the range that we operate in, 1 atmosphere. That's where the ideal gas equation usually holds correctly. As you go further away from the low pressure condition, these curves all start to deviate. So as a result, van der Waals came up with an equation to express the behavior of real gases. I want to emphasize the difference here between ideal and real gas. We're not talking about different type of gas. We're not talking about ideal being, let's say, helium, and then real being some other gas like argon. We're really talking about the same gas. Under a low pressure condition, helium will behave ideally. Under high pressure condition, helium will behave like a real gas. So we're going to start here with the ideal gas equation itself. The ideal gas equation, of course, is PV equals nRT. So we're going to change that and write it as P equals nRT over V. What happens when we start increasing pressure, there's more and more particles. Initially, I imagine the situation to be ideal, where I have, say, 2 gas particles, and this is the containers. Obviously, the volume of the container is relatively large. The gas particles are very far away from each other, and for all intents and purposes, they don't occupy any volume, right? Because they're so small, okay? Now, when I increase pressure, really what I mean is that I either make the volume smaller, the whole container smaller, I increase the number of gas particles. So let's say it's the same container, but now I have a lot more gas particles, okay? Now, at this point, you can no longer ignore the volume of the gas particles, okay? In the real gas condition, you have to worry about the volume of all of these other gases. The volume that's available to a gas in the real condition would be the volume of the container minus the volume of the other gas particles here. And starting with the ideal gas equation, which is right here, he said that in order to correct for that volume effect, I need to subtract the volume of the other gases. How do I get the volume of the other gases? Well, he said that I need to know number of moles of all the gases that I have here, right? So that's counting the number of particles. And then I'm going to multiply this by what we call the volume factor. So this is often called the van der Waals constant B. This is a measure of the volume of a particle, and values of B has been measured for many different gas particles. But basically, he's saying that if you want to correct for the volume, you're going to have to subtract that volume of the container by this NB quantity, which corresponds to the volume of all the other gases that occupy that same volume container, okay? And so we start initially with P equals nRT over V. Now we subtract from the V is N times B, where N is the number of moles and B here is what we call the volume factor for each gas. So now we're going to talk about the second correction. When we have a lot more particles, if these particles are not moving very fast, that would mean that at lower temperature, right, because temperature corresponds to speed, there are a lot more chances that they will make some kind of intermolecular attraction. Again, compared to the ideal case where there's only one or two particles in a volume of this size, and chances are they're not going to make any kind of interaction because they're moving fast and there's a lot of distance between them. But now the distance between them is a lot shorter and they're moving more slowly. Okay, so that's why temperature is also a factor in making the condition less ideal. If these particles are making interaction with each other, we no longer can make the assumption that the particles will hit the wall with as much force as it would in the ideal case. We total all of those hits or collisions, and we call the total number of collisions the pressure of the gas sample. Okay, these particles are interacting with each other. They're still going to hit the wall, but they're not going to hit the wall with as strong a force as they had before, because now the interaction is cutting down on some of that force that they originally have if they don't have any interaction, like in the ideal case. Okay, so what's that going to result in terms of the equation? Now earlier we had it corrected for volume. Now we're going to do correction for pressure. Okay, because as you can see in our explanation just now, the factor that's going to be affected most is the pressure. What we say is that this is the pressure if there's no intermolecular interaction. If you have intermolecular interaction, you're going to have to subtract from that pressure a certain amount of pressure that's lost. So we put a negative sign here to subtract. The amount of interaction that happens will be due to the concentration of the gas that you have in there. And concentration, of course, is N over V. And because of reasons of dealing with large number of particles, this quantity is actually squared. Concentration is then multiplied by this factor here, which is called A. Okay, now you notice that earlier we used this constant B, now we use this constant A, and that is often called the van der Waals constant A, and that basically is a measure of the strength of intermolecular interaction. The stronger the attraction is, the larger the value of A, which means that the more you subtract the pressure, right? P equals nRT over V minus NB minus A times N over V squared. This is what we refer to as the real gas equation. Remember, the ideal gas equation would just be P nRT over V. Okay, this is often also called the van der Waals. Again, I just abbreviate van der Waals name, VDW, van der Waals real gas equation or van der Waals equation. So again, I want to highlight the actual experimental measurements for these behavior changes, right, in terms of real versus ideal gas. So here you can see actually a sample of argon compared to a sample of an ideal gas, right? So the x-axis here is pressure. As pressure goes up, that argon starts to change its molar volume, different than what we would expect for an ideal gas. And here's the effect as a result of intermolecular forces. Here's xenon in the green, and then here's the ideal gas comparison in red. The xenon curve start to move away from the ideal gas curve as you go to lower and lower temperature. So the x-axis here is temperature. I want to mention that we had these two constants called the A and the B constants in the van der Waals equation, where A is a measure of intermolecular interaction, and in this specific case we really care mostly about attraction. So how strongly are these gas particles attracting each other, because the attraction is what's cutting down the total pressure of the gas. The second thing you can look here is B, right? That's a measure of the size of the particle. So the larger B is, the more volume it's taking up in the container, and as a result the more you have to worry about the gases behaving less ideally. Both of these factors are roughly correlated with molar mass, because the larger a gas particle is, generally the more electrons and protons it has, and as a result you're going to have more electrostatic interaction. Also, of course, the larger the molar mass, usually you tend to get larger size as well. So I'm going to work through an example of calculating pressure in this case using the ideal gas and the van der Waals equation. The problem itself asks for us to calculate the pressure of ethanol at 82 degrees Celsius if you have 1 mole and it occupies 35 liters. And it's asking you to calculate it both ways using the ideal gas equation and van der Waals equation and compare your answers as a result, because remember that we want to see if is there a big deviation when we're using one equation versus the other one. So if I want to use the ideal gas equation, of course I have to write the ideal gas equation, which is PV equals nRT, and I'm just going to write it as P equals nRT over V because I'm being asked to calculate pressure. And if I substitute all of these numbers in here, which is 1 mole, 0.0821 liter atmosphere per mole Kelvin, and then we have our temperature, and that's equal to 355 Kelvin. And lastly, we have our volume, which is 35 liters. What you should get is 0.833 atmosphere. That is if you assume ideal condition. Now let's say we try to calculate the same situation with the real gas equation. So remember that the real gas equation is P is nRT over V, and then you subtract NB, and then from there we subtract that pressure from this other term, which is A N over V, and then the N over V is being squared. Okay, so let me just calculate these two components separately just so that I have space to make this calculation. So if I were to calculate the nRT over V minus NB first, I'm gonna just plug in the numbers here. 1 mole again for N, and then 0.0821 liter atmosphere per mole Kelvin, and then 355 Kelvin is my temperature, and then the denominator in this case is volume, which is 35 liter, minus the N times B. So N is 1 mole, that's just the number of moles, and B in this case is given as 0.08407 liters per mole, so that's what I'm gonna put in my numbers here. When you multiply these two numbers together, the moles will cancel out, so that works out to be just liter at the bottom, so then you have liter subtracting with liter. At the top you have mole canceling and you have Kelvin canceling, and then of course at the end you have liter atmosphere on the top and liters at the bottom, so the liters will cancel, leaving you just with atmosphere. Okay, so that's what you have there in your calculation. You just have atmosphere for this term. You should get 0.8347 atmosphere. This is just the first part of the equation. Now I have to go and calculate the second part of the equation, so let's do that. So let's calculate that at the bottom here. So the second part of the equation is A N over V squared. The A value again is actually given in that question. So if you look back here, it shows 12.02 with the appropriate units. So I'm gonna just copy that number here. Now you notice that if you work this out with the units here, you have 1 mole of your gas, and then the volume, remember, is just the V that's provided, which is 35 liters, and you square this component. Okay, now you notice that what happens is if you work out the units, this mole squared becomes mole squared, and that cancel with the bottom mole squared here, and then the liter of course cancel with the liter square here, liter square also, so you're left again with actually just units of atmosphere. And I made a mistake here when copying. The atmosphere here should be at the top. Okay, so liter square atmosphere per mole square. Okay, so then your N unit is just atmosphere in your answer, and what you find is that the answer is 9.81 times 10 to the minus 3, or another way to write it in decimal terms, which is 0.0098 atmosphere. Okay, so then what we have to do to calculate the pressure, remember from the initial equation, we're going to subtract this number right here that we calculated earlier minus this number, and the result, if you do that calculation, is 0.825 atmosphere. Okay, so again, just to compare this with the ideal gas calculation, so earlier we had this number right here at the top, right, 0.833. So there is a difference in terms of value as we expect. When we assume that this is real gas condition, the pressure is less than what we expect from ideal gas. That hopefully shows you how to utilize this question. It's really just kind of plugging into the formula and calculating it. And this is the end of the gas topic. Is this